Welcome back, Math 170. We're looking at section 3.3. What does the first derivative and the second derivative say about the original function? If you remember from section 2.2, we did a little graph sketching to help us analyze this a little bit more. So we're going to revisit this and then kind of give you some concrete details to go along with this. So let's revisit. When the derivative was positive, remember, let's see if I can, just a quick sketch to get us on the right page. So just maybe we have something that looks like this. And if we were drawing tangent segments, we noticed that when we had positive slopes of these tangents, we realized that the function was increasing. And then if we did the same idea, different points along the particular graph, and we noticed that the slopes of the tangents were negative, we would imply that the function is decreasing everywhere in the interval. And then remember, if we were speaking about the derivative being 0, well, we kind of know from the last section, your function may have a local min or a local max. But it's unclear just by looking at the derivative what it would be. We would have to investigate. So this is where the first derivative test comes into mind. It really does help us see without having to actually graph. So we're going to first suppose that C is a critical number of a continuous function f. And so I know that's the English version of everything. You have to remember, what does it mean to be a critical number? Remember the two criteria, two things. This is the one everyone kind of understands. The derivative evaluated at that point is 0, but also there's a possibility that the derivative evaluated at that point could be undefined. So we want to be careful. We don't know for sure all the time about the undefined part, so let's keep that in mind. But they're trying to tell us if the sign of the derivative changes from positive to negative at the point x equals c, then f should have a local maximum at c. And I'm going to just illustrate with the graph, kind of like the one we just drew. It's not always that you have to memorize this. You might be able to make sense of it if you kind of know what everything's going. So let's say we have C, and I'm looking at having a local maximum, so I'll kind of be maybe drawing something that faces downwards. So at x equals C, I mean, we can visualize it if I drew it correctly. Oh, let's make it a little prettier. There we go. So if you have the picture of the function in front of you, no problem. We can kind of see, oh yeah, that does look like a max. But when we're dealing with f and we're trying to understand slopes of tangent lines, remember, if we were drawing these tangent segments along the function, we would realize that the derivatives were greater than 0 in this region. And if they are, that's indicating about the increasing part. So that's where we're getting, oops, sorry about that. The increasing. And a lot of times we like to abbreviate with INC. If you don't mind, I don't mind. So also, just like we were drawing earlier, we notice beyond the point x equals c, the slopes of the tangents are negative. So we can clearly say that the derivative is less than 0 in this region. So that's where we imply that we have decreasing function. Now, I'm using the notation f prime greater than 0, f prime less than 0. At this point, because you're only dealing with one derivative at a time, you can look at plus and minus, but always be careful to understand what you're analyzing. So we'll kind of have an issue later when we speak about it. So you can kind of see, oh, I mean, it does make sense visually. If you're going from increasing to decreasing, you could even visualize it well. I know I have to go to a graph. Eventually, I have to make a decrease. I mean, that does make sense. You're going to have this local max at this point. So kind of think of it that way in a sense of not having to memorize so much. So you can probably guess what's going to happen if we end up having a graph. And at x equals c, give you an idea. Let's suppose the sign of the derivative changes from negative to positive. And so if we can kind of do a quick sketch just so you see, you kind of are guessing, yes, we are going to have a local minimum at the point x equals c. But then just reason with yourself why, so that we can be clear about this. So if we kind of go with, again, graphing mini tangent segments, on this side of the c, I should say the left side of the c, your derivative is less than 0. If you prefer, you can think about it as negative. On the right side of the c, if you draw your segments, you know that the derivative at every single point is always positive. So you could kind of see that, well, when the derivative is negative, we have the decreasing portion of our function. When the derivative is positive, we have the increasing portion of our function. And so a lot of times when you're trying to interpret, if you're going from decreasing to increasing, well, think about what you would think about. Well, the function's decreasing. Eventually we have to make it increase. We end up having that local min. So sometimes that helps too. Now remember, we're talking about the sign of the first derivative, hence the name of the first derivative test, to give you information about the original function f. So look at that. And then I also want to give you a little note, because this is where we run into the confusion. If you had no sign change, well, you can think about it. If you're always decreasing, oh, whoops, here we go. If you're always decreasing, there's not going to be a min, or if you're always increasing, there's not going to be a max. We don't know where it is. So if there's no sign change, there is no local min or local max. And kind of an idea of this, if this would kind of maybe bring the concept home, I like to be visual. You know, let's say we have a critical point. Well, we can try to look at it this way. And let's say I have one of those. I think we were playing with one of these earlier. I'll do my best. Something kind of along of a cubic function, maybe a cubic function. And so if you look at what's the behavior around the point x equals c, we can judge for ourselves that, oh yeah, looks like the derivative, all these little derivative tangents, we should be positive. But it doesn't change, because if you keep drawing your tangents, you still have positive slopes. So you can look at this as going from increasing to increasing, i.e. positive to positive. And then, of course, we do not see a local min or local max. And then maybe another example might be, maybe some of those rational functions coming back. Sometimes we'll see, let's draw that a little prettier. Here we go. So let's say we have a function, those fancy rational functions. And in both cases, I can see on the right side, I'll start off with that, I'm clearly decreasing. And if you were to calculate your derivatives are less than 0 or negative in that region. But also, if you were to look at the left side, all the slopes of the tangents are also negative. So you have decreasing as well. And so here you can see, oh, that looks like to be where the derivative might be undefined. And that's going to give you a heads up. There's no local min, there's no local max. So let's put this into play with a more exciting example. We're going to try to find all local extrema for the polynomial f of x equals 3x to the 4th minus 4x cubed minus 12x squared plus 5. And then from that, they just want us to sketch the graph. And I know we've analyzed polynomials in pre-calculus class, but this gives us a much nicer way to interpret where we're having our highs and lows. So let's start off. If I'm looking at finding extrema, I really want to look at finding all of the critical numbers. So that's the first thing I'm going to look for. So find all critical numbers of your f. And anytime I'm dealing with critical numbers, usually we are looking at that first derivative. So that's the first thing I'll calculate. First derivative. And maybe I'll be a little bit more formal. It was f of x, so we should say f prime of x. And if I'm taking the derivative, I should have, let's see, 3x to the 4th, we should have 12x cubed minus 12x squared minus 24x. So that is the first derivative. And generally, when you are looking for critical numbers, you're either going to set the first derivative to 0 or find out where it's undefined. Well, polynomials are never undefined. So this is the only route we can take. We're going to set this equal to 0. See if we can solve it. And I know it's a cubic function at this point, but I do see some very, very nice GCFs there. So 12x I can factor out. That's pleasing. That leaves us with an x squared minus x minus 2, still equal to 0. And that's a very nice polynomial that we can further factor down. So we have x minus 2x plus 1, still equaling 0. And now you have 3 solutions. The 12x, so 12 times x, the x was in the factor, so x should be equal to 0. We have another case of x equals positive 2 or x equals negative 1. So there's 3 critical points in this function. And a lot of times what I'll do is I will actually kind of create a mini number line to help me analyze this a little bit nicer. So what I like to do, I'm going to arrange everyone in ascending order on the number line. Might as well write out the steps. Obviously, you want to put the numbers in order. Wouldn't make sense not to. And so leave yourself a little room for this sketch. I'm going to write it off to the right just because. And so you don't have to necessarily make the numbers all to scale, but just kind of mark their general location. So I should have negative 1, 0 might be somewhere over here, and then 2 might be somewhere over here. So I've got my number line. And what I'd like to do is kind of keep in mind that these are critical numbers that are separating the x-axis into, what is that, 4 different regions. So I know we kind of played with this in section 2.2. Maybe this will bring the concept home a little bit more. And what I'd like to do at this point is I want to know what's happening with my particular derivative. Is my derivative positive or negative in each of these regions? So that's what I'm going to do next. I'm going to select a version. Of the derivative. And I'm using test points in each region. And that's going to help us determine the sign of each region. And so this is kind of why I was so, I don't know if any of you had me for pre-calc or college algebra, but I was really big on the sign analysis method because I knew stuff like this was coming, and then this will be second nature now. But if not, we practice. So remember, this is not about the original function. So I'm going to emphasize that I am trying to talk about the derivative. So I want to be extremely careful here. And if you're trying to find a test point in each region, no problem, we can do that. And so what I'd like to do is plug in, and I'll kind of write out what my thoughts are, is I'm looking at the first derivative evaluated at, let's see, the region on the far left, maybe, you know, -2 or -3 or -10 might work. So I want to look at, let's write that a little nicer. Sorry about that. I want to look at what is the derivative evaluated at this point. And let's say if I'm looking in between -1 and 0, I want what's the derivative evaluated at, you know, maybe -1/2 or 0.5. Then my next region over, in between 0 and 2, 1 tends to be popular. And in between, well, I should say in between, from 2 and on out, you can pick any number, but just find a test point. So, you know, 3 might be very popular. And when we do this, the polynomial of the first derivative, if you're kind of looking at it right now, you could use this version, you could use this version or this version. It kind of depends if you have a TI or not. If you don't have a graphing calculator to nicely plug things in, I might choose the simplified factored version. So we can do that now or later, it's up to you. But I kind of prefer to pull the TI up just so that I can analyze this a little bit later. I don't think in our class we don't necessarily take anything away from you. Let's see if we can open that up. Our TI music playing if we had some. And what I like to do for these types of problems is I am eventually going to be analyzing the original function. So I like to enter in my original function first and then my first derivative, and just keep track of who you're calling y1, y2. I kind of do this by colors, so I'm kind of lucky to have this, the smart view, but feel free. Kind of just keep in mind, make notes to yourself, because eventually they're going to ask questions about the original function. So might as well type it in right away. Not 3x to the 44. Let's clean this up. Now, I like to point out a lot of you have experience in pre-calc and college algebra, and you already know how to graph polynomials and find maxes and mins using your TI. But that's not the purpose of this particular section. They want you to kind of look at it analytically. So yes, you can find the correct answer, but if you can't prove the calculus behind it, you would not get credit. So be careful. So I have 3x to the 4th minus 4x cubed minus 12x squared plus 5. And then we always look back to make sure we've entered everything correct, double check, triple check. So that's the original function. And now my derivative is 12x cubed minus 12x squared minus 24x. And I believe that's it. Don't forget that x though. Okay. So remember, what we were trying to find, and I'll switch back so we can refresh our memories. You guys can see. We were trying to find the first derivative evaluated at -2, -0.5, +1, and 3, or whatever choices you had in the first place. So moving back to the TI, this is where I utilize that table feature. Yes, you can play with the function, but we already have the table set up. And so you can quickly enter in all of your values that we were speaking about, -2, -1/2, +1, and 3. And you just analyze what's happening with the first derivative. What is the sign of our answer? And let's make sure. I want to double check. Doing this. Something is looking a little bit off, so I want to make sure. Particularly, let me make sure I've entered all the signs in right. I was wondering, why are those numbers so large? Well, I don't have anyone here to stop me from missing a separation of two terms. Wasn't that 12x cubed minus 12x squared? Leica, anything to add? No, she's sleeping too. Okay. Yeah, so sometimes you just have to make sense of like, why are we getting such huge numbers? So let's see, 12x cubed minus 12x squared minus 24x. Let's go back to the table now. Let's press enter first. That would be ideal. Sometimes there's good things about having the TI on the computer, but there's also bad things is that sometimes it is not responsive or too responsive. My apologies. And this gives us time to also play along at home. So minus 24x. Double check, triple check. 12x cubed minus 12x squared minus 24x. Now I'm feeling pretty good. Okay, go back to the table. Now the numbers aren't so crazy for those numbers that I picked, -2, -0.5, 1, and 3. And just keep in mind, we are looking at y2, not y1. y1 would be the original function. So take note, you don't really have to find the value. We just want to know whether the derivative is positive or negative. So take a mental snapshot or write it quickly down. I'm going to go back to my screen so I can compare. But I should be getting The first derivative evaluated at -2, I should be getting a negative. This is where I'm thinking. The first derivative is negative here. At 0.5, if you look at the graph for the y2's one more time, we're getting positives. And at 1, we're getting negative. And at 2, we are getting positive. And I want you to be careful. Back when we were in pre-calculus and we were dealing with sign analysis, there was a pattern when you were dealing with polynomials about, like, so a lot of times you were seeing, oh, there's alternating signs. And that is true, but we have to be careful. We are not finding the signs for the original polynomial. We're finding the signs for the derivative. So I have to emphasize, don't make assumptions about signs changes in the first derivative. If you saw earlier, sometimes signs do not change as you're moving beyond your critical points. So that's something we have to get used to. And there's my warning. Okay, so we selected a version of the derivative. We used test points in each region to determine the sign of the region for the first derivative. I have to make sure that you are clear on that. And then now you're going to use the first derivative test. And maybe before, I don't know if you want to reemphasize this for yourself. Now that you know that the derivative is negative in each region, you may want to speak about whether or not you're decreasing or increasing. Sometimes those English cues help us. And that might help us with this first derivative test. So that's what I'm going to do at this point. So let's use the first derivative test. And so basically we're looking at the behavior at each critical point. So first critical point, at x equals -1. Now keep in mind that when we're describing the language, we are dealing with what is happening to f. So maybe I'll recolor code those so that you're not confused. So notice when the derivative is negative, the actual function is decreasing in the region. When the derivative is positive, the actual function is increasing. So at x equals 1, the function goes from decreasing to increasing. Or you can think about it in signs, negative to positive. But I like to kind of draw a little picture, decreasing to increasing. So what do you think happens? Well, if that's the case, we've got ourselves a local min. And what you want to describe with the local min is it's the local min evaluated at the critical point. And so the critical point was -1. And so I need to be a little clear. Keep in mind, I know you plugged in stuff for the derivatives, but we're looking at the actual critical points at this point in time. Now, good news for us, if we've already entered our ideas on the calculator, you don't have to go back and plug into original function and do all the extra math. But I'll get there in a second. I want to do them all at once so that we don't have to keep switching screens. So don't forget, we're going to have to find this value. But at least we know the location of it. It's at x equals -1. So we're going to do the same thing. The next critical point at x equals, I believe that's 0. Maybe I'll save a little space. I'll move to the right. So at x equals 0, let's look at the behavior of our function. F is going from increasing to decreasing. So you could probably guess if you draw a quick little snapshot. We have ourselves a local max where the function itself, the original function, is evaluated at 0. And then, last critical point, at x equals 2, our function is going from decreasing to increasing. So you can draw a quick little sketch for yourself. That means we have a local min. And it's at the function itself evaluated at 2. And so this would be a good point. This would be a good place to use the TI to find the y values. So let's switch back. So now I'm on my TI and I'm on my table, and I just want to be careful. Remember who you defined. Y1 is the actual function, Y2 is the first derivative. So if you don't have color codes to make that stand out in your mind, make a little note to yourself on paper. And we want to know what's happening at -1, 0, and 2. Voila. Notice, then this kind of also puts the concept into play. When you look at y2, your first derivative, that's where it was 0. So that's kind of clear. Oh yeah, that means that we have some critical points going on. And now you just take your y values. So let's write those in. You take a snapshot or write them right down. I'm going to switch back. And now we have the actual location of our local extrema. So we should have the function evaluated at -1 happen to be 0. The function evaluated at 0 happened to be 5. And the function evaluated at 2 is actually -27. So this right here, we just found our local extrema. Now, feeling pretty good. I have a lot of information going on. They wanted us to find all local extrema. Check, got that. Oh, and then sketch the graph. Now, at this point, I'm not too concerned about you being able to mentally sketch. I know you've been tested on that from your pre-calc or college algebra classes, but I just want to point out that a few things that we're pulling from our past really help us get an accurate graph without even having to look at our TI. So let me kind of draw that on the side. Of course, you're able to use your TI to get a little more accuracy. And I know you can use your TI to verify the maxes and the mins, but make sure you're showing the work for that. That's important. So what I'm noticing is I'm saying, okay, I want to start with plotting maybe my local extrema. So I'm going to sketch, and this is 2 dimensions. So let's draw this off to the side. Draw myself some axes. I don't know if you can see the graph paper. I have it online. But I start with plotting the local extrema. Let's spell plot correctly. What's going on with me today? So if I'm looking at things, I want to say, okay, the local extrema, f of -1 equals 0, so I'll mark it. So -1, we have 0. And then I'm saying what's happening at f of 0, we should have a 5. 1, 2, 3, 4, 5. And at f of 2, we have, we have a negative 27. So my friends, if I'm doing this scale by 1, we're going to have a quite large graph. So I'm going to exaggerate a little bit. And negative 27, maybe we'll assume it's way down here. Of course, we know it's not quite to scale, but we do know it's extremely lower than our other points. Now, a lot of times for myself, I like to draw mini arcs to help me with maxes and mins. So if I go back to my local extrema, I had a local min at negative 1, 0. So I know that I should have something like this. I had a local max at x equals 0. And then another local min at x equals 2. So it kind of gives me an idea. Now, along with this and a little bit of fun from your past, endpoint behavior of polynomials. That's kind of really neat that we know where to stop and start. But if I'm looking at my original polynomial, if it will let me, there we go. The degree is 4, and we have a positive leading term. So a little note, when you have an even degree, you either have an up-up behavior or a down-down behavior. When the leading term is positive, that further narrows down your endpoint behavior. So this is where we're getting the up-up from. So what does that mean? It means the far edges of your polynomial, pretty much as x approaches positive infinity, x approaches negative infinity, we're going to have up, up. So we're going to have the y values approach infinity in both cases. So if we have up behavior, what happens is you're starting somewhere from the top, making sure you end up going through your arcs. If you go through your arc at x equals negative 1, you have to come back up again, come back down again. And if we wanted to, we probably could find the 0, a little more accuracy. But then we still have to end up at the end. Hence the behavior, up, up. Now, we might not know, we can find these with our TI, and we can probably find, maybe I'll mark them in orange. The zeros can be found with the TI or by setting your original polynomial equal to 0. Depends how accurate they want this from you, but if you're looking for a relatively accurate sketch, I'm not quite sure where they're at, but we can compare now. Pretty cool, huh? Really nice. We can graph some really complicated polynomials. Let's check what that graph looks like. We already have it entered in our TI, and that's kind of the point of this, is that's why we're not spending too much time on being accurate. We have technology now. And back when they wrote this book a long time ago, I mean, this is the 8th edition. It's been around quite a few years. So it's good to know to do things by hand, because sometimes different professors will take away the TI, and that's fine. It's good to analyze. So let's go to graph. I'm going to go to y equals first because I don't really want to see the first derivative. So I'm going to unselect that. And I'm going to graph it. And I'm probably in a 10 by 10 window. Oh, I'm even worse. Well, I'm going to zoom out a little bit. And let's zoom out a little bit more. Maybe that's too much. But you guys can see, I'm really excited about that. You can actually see the shape of our particular polynomial. We're pretty accurate with our graphs. And we actually know how low to make the window because we already know that the absolute min, or I should say local min, is supposed to be like a negative 27. So let's just make our y min negative 30. And now you have a great way to get your accurate picture. So sometimes having these bits of information of stuff to do by hand does also help out on the calculator. Pretty cool, huh? Awesome. So let's go back. We're going to build on this. You're probably wondering, well, let's go back and kind of remember what we're doing in the first place. And let's sketch ourselves a picture. I'm going to do kind of more of a wavy. All right. And just kind of pick maybe 5 points along the graph. So maybe I'll pick something here. Maybe I'll pick something here. Maybe something over here. Over here. Maybe I'll do something over here. Oops, that last graph. I guess I wasn't looking that carefully. Here we go. All right. And so if you pick, like, you can pick as many points as you like. I don't care. But if you sketch little tangent segments, kind of allowing you to see what's happening with the slopes of the tangents along the way. That wasn't a pretty one, but I guess you'll get the picture. And do as many as you want to help you see this. But they're kind of giving us a definition in a different sense. Is if you're looking at these tangent segments that you've been plotting, you could kind of see there's points for certain tangent segments. The graph is below the tangent segment, and for certain tangent segments, the graph is above. So the blue line is above the red lines, or the blue line is below the red lines. And the definition of what this means, if you want to speak more mathy, they call this concavity. And depending on the location of your tangent line versus your graph, you can either be concave up or concave down. And so if we look at this, and I'll give you something over here. I'm going to cut it where it's in half just a little bit. Give you a point along the way. But if you notice, if I can give you a reference point, everything to the left of A at this point, you see that the function is below the tangent. See how blue line below red line, or blue curve below red line. And when that is the case, formal definition, we call this concave down, or a lot of times people will abbreviate it CD. Now, if you look at the right of A, look at the curve. The blue curve is above all your tangents. And we call this, guess what? Concave up, CU. And if we can kind of look at this a little more precisely, you probably already knew this when you were dealing with parabolas. A lot of times they would say, hey, is the parabola frowning or smiling? And you're like, oh, it's frowning. That's concave down. It's just kind of a less mathy way to say that. If the parabola is smiling, concave up. So we can talk about portions along polynomials or other curves in this manner as well. And so the reason why I kind of drew the A is because if we look at this carefully, if you keep drawing a lot of slope tangents, there's a point where all of a sudden the slope tangents change from positive to negative or negative to positive. And that's an important point to us. So F changes concavity at the point A, comma, F of A. And this point has a special name. They call this the inflection point. And inflection points are really valuable. I see a lot of applications in economics. We have them other places, and you'll have your chance to explore them in this chapter. But something that comes to mind when I took my economics classes is the point of diminishing returns. And that's kind of what an inflection point is. So I'll let you explore that if any of you are into that. But right now we're just getting into the calculus behind it. So, you know, there's a lot of cool things we can see. We can look at the graph and you can visualize, oh yeah, it's concave up, it's concave down. But you might not know the precise point of inflection. And you've probably guessed it, hey, there's a mathy way to do this. Very similar to, you know, we knew when we had maxes and mins, we can visualize them, we can see them, but there's an actual calculus way to get the precise value. So that's what the concavity test tells us. And it has to do with the second derivative. So if we're looking at the second derivative, it gives us even more information about the graph. And it kind of makes sense according to whether you're getting a positive or negative. If your second derivative is positive, you have concave up. And that's where we use the CU from. And if your second derivative is negative, then you're concave down. And CD. There we go. So we can then take our function if we were interested, and we can find if there's any points of inflections or anything like that. And yeah, there's a lot of cool things we can play with. So just kind of keep in mind what happens when your second derivative is equal to 0. That's usually where your A is. So it's a important number in terms of how you're getting these boundaries. How do you know when you have second derivative negative region and second derivative positive region? That's where our A is coming from. So you're guessing, once I take the second derivative, I'm going to set it equal to 0 and then play from there. And you are right. Now, another thing, a little application of a second derivative, if you were interested, to me, it's fine. You don't really have to use this because the first derivative test gives you the same information. But the second derivative also has some applications to whether you have local maxes or local mins. So feel free to use this, or if the directions in the homework make you practice it, then we would have this. But they're trying to tell us that if the second derivative is negative, then your function, your original function itself, should have a local max at that point. And kind of think about this. The second derivative negative. So when we kind of look at what it means for concavity, if the second derivative is negative, you're concave down. We'll look at the left side of the graph we just drew. I mean, yeah, there's going to be a max somewhere. So that kind of gives us an idea. I mean, it's kind of intuitive, but just in case you want to refer back to this later, the reason is that your CD, your concave down at your x equals c. And what does that look like? Cute little maximum. And similarly, if your second derivative is greater than 0, you've got yourself a local min. Kind of look at it again. See how you're concave up? Well, yeah, you are concave up at x equals c. And what does that look like? It's kind of a smile. And if you need something else to kind of help you, I mean, sometimes making cute little things for yourself are nice, but remember, what do we have? Second derivative positive. There's 2 plus signs. Got ourselves a little happy face, but that's a local min. Our second derivative negative, 2 negative signs. Got ourselves a sort of sad face with closed eyes, I guess, but that is a local max. So I don't know if that helps, but I always like drawing cute little pictures. It makes my math notes such cheery place to refer back to. But do it whatever you can. I know sometimes some things stick for me and some things don't. But just to apply this back to the example we've already been studying, just so that you guys can see the second derivative test. And this is a case where you'd be expected to use it because of the actual directions. They want you to demonstrate it. So let's kind of remember that, well, if they want us to use the second derivative, the first thing we've got to do is find that second derivative. So before you find a second derivative, you got to make sure you know the first derivative. And we already found that earlier. 12x cubed minus 12x squared minus 24x. And then our second derivative at this point is just taking, keep going. Derivative of 12x cubed is 36x squared minus 24x. And then now derivative of negative 24x is negative 24. And if you're playing around with where the critical numbers are, don't forget, we found them already. Critical numbers. They were already x equals -1, x equals 0, and x equals 2. So if we're using the second derivative test, the idea is you're evaluating your second derivative at your critical numbers. C standing for critical numbers. So I like to set this up just so that you see it. What would that look like? We would have the second derivative evaluated at -1, the second derivative evaluated at 0, and the second derivative evaluated at 2. So let's find those points. Now this isn't horrible. You can definitely plug them in, but I'll pull up the TI since I already have everything. I didn't enter the second derivative, but I can definitely do that. Sometimes I really like to save my brain power for the calculus instead of the computation. So that's just my preference. But let me go back to y equals. I can deselect things or reselect things if I want to see them, but I just want to point out that I'd be entering y3 this time as the second derivative. Now that could be confusing. I just thought of that. Well, just keep notes for yourself. Remember, y1 is the first function, y2 is the first derivative, and y3 is the second derivative. Sorry, there's no way to rename them at this point. 36x squared. And if that confuses you and you don't like the TI, plug it in by hand, no problem. Minus 24. Here we go. Okay, just make sure. I feel good about that. Press enter. Let's do the table. I probably already entered them in when I was finding those extrema. -102. So notice we have 3 different function values. And here we are looking at the y3 this time because that is the second derivative. So at -1, y3 is 36. At 0, y3 is -24. And at 2, y3 is 72. I'll copy my results over to my paper now. Remind myself, it was 36, then -24, and then it was 72. You don't really have to care too much about the numbers, but it's nice to show. But then all you have to do at this point is just say, are you positive or negative? Well, 36 is greater than 0, negative 24 is less than 0, and 72 is greater than 0. So now, remember, if the second derivative is positive, that means you're concave up. So that helps you, if you remember the concave up. And concave ups, they look like smiley faces. So that should tell you that your y value, f of, and let me highlight that, we are looking at the function itself. F of -1 is a local, if you're smiling, it has to be a local min. That's their lowest point. Similarly, your function evaluated at 2, f of 2 is a local max. Why did I say max? I meant min. Why again? Because we're concave up. Who is the local max? This guy, the one in the middle, f of 0. So because our second derivative is less than 0, we got concave down. That looks like this. And so that tells us that we got the local max. So that tells us the original function evaluated at 0 is the local max. And so that's another way to classify what your extrema are. And kind of depends, you can, sometimes it's a lot cleaner. I guess it depends how complicated it would be to take the second derivative. Because I mean, that took a lot less work than us playing around over here, because we still had to do signs. But still, in all senses, it's still valuable. I kind of like this part too, because when I do the signs, I can tell the function is decreasing to increasing. And I already knew that the slopes are 0 at the critical points because we're polynomials. So I kind of have this sketch of my function. Oops, I should probably draw it correctly. So decreasing to increasing looks like this. Increasing to decreasing looks like this. Decreasing to increasing looks like this. It also kind of hones in like, there's some application here. How do we know if we have maxes or mins? It kind of gives you a nice picture as well. So there's benefits to using both or just knowing both. Sometimes just to check yourself. That's the second derivative test. Wonderful if it's easy to plug in for second derivatives and find second derivatives. And then I kind of leave this typed in your lecture notes, but if your second derivative is equal to 0, it's possible you have an inflection point. And so if you know you have an inflection point or you're thinking you do, just do a sign test on both sides so that you can kind of tell. In our case, we already knew we had a polynomial, but we'll play with it. Example 3 will give you an idea, and you kind of have an idea of what these functions may look like already. That's kind of why we wanted you to review it chapter 1 and go through all that. But now we can show you the calculus behind it. So, example 3, they want us to find all inflection points. And inflection points always have to do with some sort of relationship to the second derivative. So that's the first thing we've got to play with. Well, let's find the first derivative. Okay, so that would be kind of 3 times x minus 1 squared. We'll have to multiply by 1x or the coefficient of x because it will not change anything. We can then take the second derivative. So it's going to be 3 times 2, 6 times x minus 1. No need for a chain because that derivative of the inside is still 1. And that's going to help us see if we have an actual solution. So if we set this equal to 0, we should get x equals negative, or x minus 1 equals 0. That gives us x equals positive 1. So now we have a possibility. He's potential. Okay, so be careful. Potential inflection point. Before we make that decision, we do a quick little sign check. So I there's where my charts come back into place. So we test. we test. Come on, there we go. Okay, so here's my quick number line. I have my potential point of inflection. And remember, I'm looking at the second derivative. Okay, so the second derivative is going to give me the information about the sign. And then this is a case where, okay, this is not too bad. We can plug in points on each side of the second derivative. That is this part right here. So if I were to pick, and maybe I'll separate the regions just so we can see a little prettier. If I were to pick a point on the left, x equals 0. So just so that you can see, this is what I'm doing. So I'm plugging in to the second derivative. I get 6 times -1, which is negative. So that tells me that the second derivative is negative in this region. And what does that tell me about my function itself? It tells me that function itself is concave down. You don't necessarily have to name this, what's happening to the function, but it's all related anyways, might as well. Same story. We're going to take something on the other side of the 1 and plug that in. So what is that? F double prime, let's do 2, might as well. So what does that equal to? 6 times 2 minus 1, and you can probably already tell that's positive. So the second derivative is positive in this region. That tells you that f is concave up. And all we're looking for is a change. Did you have a change of signs? Yes, we did. We went from positive to negative, or concave down to concave up. So we have a change of concavity. So therefore, now we could answer f has an inflection point for sure. And then what would be the x value? So it's x equals 1, but if we're talking about f, we're saying what's f of 1, and we already know it's 2. Or if you want to name the actual coordinate, what is that? 1, 2. So remember, everything you're doing with derivatives is always giving you information back about the original function. You may be plugging in numbers to the derivatives, but those are test points to tell about the signs, certain regions, increasing, decreasing, etc. So kind of be careful. That tends to get mixed up, especially if there's a lot of things on your mind, as there might be in calculus class. But let's do one more to make sure we feel pretty confident about this. And then we're going to do a little analytic geometry, bring that back into focus. So let's do the same idea. We're looking for inflection points if there are. I'm going to first calculate the second derivative, but before I do that, I got to calculate the first derivative. So this will give me 4 times x minus 1. And that's 4 minus 3. That's it's going to be, excuse me, x minus 1 cubed. Now second derivative, g prime prime x. That should be 4 times 3, 12 times x minus 1 squared. Now to find potential, we're going to set our second derivative equal to 0 and see what we get. We'll do a little algebra here. X minus 1 squared equals 0. I can take the, well, just in case you guys are wondering, where did that 12 go? I don't have to. I can kind of show you that I divided it out. It's a constant. Sometimes though we go too fast and we miss things along the way. If x minus 1 squared is 0, if you take the square root of both sides, you end up getting x minus 1 equals 0, and then you get x equals 1 as a potential inflection point. And then we do the same idea. We test. So we're looking at x equals 1. And then we determine what's happening to the second derivative. And so if I want to play with this, I'll go with, okay, what is the second derivative evaluated at something to the left of 1, be a 0? In our case, our second derivative, what is it, 12 times x minus 1, 12 times 0 minus 1 squared? It's going to give us 12. And that's positive. I should probably do that in red for you all. Okay, so second derivative is positive in this region. Same thing, we're going to look at something to the right of the 1, and why not a 2? Just because it's a little easier to plug in. So that gives me 12 times 2 minus 1 squared, and I already know I'm getting a positive number as well. Except it should be, yeah, the same thing actually. So then if you guys notice, there's no change. No sign change means no change of continuity. Therefore, F does not have an inflection point at all. Inflection point. That's a little bit of practice, getting our algebraic techniques down. One last thing for this section, and like I said, we want to pull in the analytic geometry to help us analyze graphs. And so for example 4, I've got the graph, and all the graphs look the same, by the way, I realize this, but they're telling you that in part A, we have the graph of the original function. Part B, we have the graph of the derivative. And part C, we have the graph of the second derivative. And so we want to be able to use all of these graphs to explain how inflection points were found. So just kind of analyze this. Sometimes it's easy to see, and sometimes it takes a little thought based on our signs. So just kind of another way to look at what we just explained. So starting off with the original function, right away, they told us we had an inflection point at x equals 1. So you can mark it if you'd like to. And then if we're talking about original function, if it helps, you just separate the x-axis, and you could kind of say, well, with original function, and when we speak about inflection points, it talks about change of concavity. Well, in the original function, we go from concave up to concave down. So there's not really much to determine at this point. You're just kind of restating what's the definition of an inflection point if you see the original graph. So that would be my reason. The graph of F it's going from concave up to concave down at x equals 1. So that's the definition of what inflection point could mean. Now a little more exciting, part B is giving you the first derivative. So we'd like to be careful here. We can't just talk about concave up and concave down because we don't see the original function in front of us. So what I need to do is I really want to mark where they're at. So they're saying that there should be inflection points at x equals 0. Notice we don't see anything. So all I'm doing is kind of separating the x-axis. And maybe instead of making a point, I could just mark it just so that we see it. So x equals 0 and x equals 2. So again, that's where this is. So all I'm doing is kind of just interpreting each region. So if I can, that's where my inflection points are located. Now, clearly, it's not an inflection point on the graph you're looking at because you are not looking at the original function. But there's a couple of things you can determine, and you can kind of determine backwards. We could kind of play with what's going on with the derivative. So if we're looking at these points at x equals 0, just by kind of playing with viewing the graph, if you want to describe this, f prime x, it appears to be decreasing. So you kind of look at all the slopes of the tangent lines along the way. Try to do this in purple. So if you look at all the slopes of the tangent lines up until x equals 0, all those slopes of the tangent lines of this graph are negative. So that means your derivative is decreasing. Now, what does that mean? If your slopes of your tangents of your derivatives, so kind of hold that in for a second. We are not just looking at the original function, we're looking slopes of tangents of the derivative. In other words, we're looking at the second derivative. Derivative of the first derivative is the second derivative. So that's telling me that if my first derivative is decreasing, it means that my second derivative should be less than 0. There's a relationship between the derivative. Okay, the other thing, keep going. If you notice also, if you look at the region of the derivative or the graph, all the slopes of those tangents of the derivative are increasing. So that means the derivative of the derivative is positive. So that's telling us that f double prime is greater than 0. And one more region to look at based on what they told us. Check out all the tangents. All these tangents are negative. So that gives us a heads up that f prime is decreasing. But that tells us the derivative of the first derivative is less than 0. So if I can kind of summarize again, we're all kind of seeing where the sign changes are coming from. Well, if you're less than 0, you're negative. Greater than 0, you're positive. Less than 0, you're negative. Yes, there's clearly a sign change for each of these points. But how do we say this, and how do we explain this and justify this? So I kind of went through this. Let's kind of put this into words. So let's first consider at x equals 0. We're going to use the first derivative to describe how we're getting the concavity and the inflection points. So at x equals 0, the first derivative changes from decreasing to increasing. So remember, that gives us information about the second derivative. So what does that say? So the second derivative changes from, what is it, concave up, or negative to positive. And that tells us, so if we know if the second derivative changes signs, that finally allows us to conclude f, the original function, goes from concave down to concave up. And therefore, that's the definition of the inflection point at that x equals 0. Now, similarly, you can make the same reasoning. It's just kind of different from here. At x equals 2, kind of recopy what you're looking at. Your f prime changes from, so it goes from increasing to decreasing. So what does that tell you about the derivative of the first derivative? This changes from, was that positive to negative? So what does that mean? We have a sign change. F goes from concave up to concave down, hence the definition of an inflection point. So here in part B, we were analyzing the derivative of the first derivative. That's the increasing, decreasing part, which then gives you the idea of the inflection points. Okay, so we'll step. If we already know the graph of the second derivative, and they give us a heads up that the original function has an inflection point at x equals -1, x equals +1, and x equals 3, I'll kind of highlight them so that you can kind of see that the original function has inflection points here. And this is the graph of the second derivative. So here we're analyzing, if you're trying to talk about inflection points, where is the second derivative positive and where is the second derivative negative? We only have to look at the graph above and below the x-axis. So if I can look at regions, I'll just kind of highlight the region on the left. Right here, all the way from -infinity to -1, it appears that the graph is above the x-axis, so that tells us that the the second derivative is greater than 0, which means it's positive. Now, if we look the region from -1 to +1, we could kind of see that the second derivative, see how all the y values are below the x-axis? So the y's are negative. And then moving forward, the region between -1 and 3, we can see that the graph is above the x-axis, so all the y values are positive. And then finishing off from 3 to infinity, the graph is below the y-axis. So that means that the picture, the y values, are negative. So here, you only have to address what's happening in the second derivative, but you had to really interpret what was the region. So if you want to kind of go through this, at x equals -1, that's the first one. All we have to do is describe the signs. F prime, double prime I should say, changes from positive to negative. So that justifies what F does in terms of concavity. It changes from concave up to concave down. And that's a definition of the inflection point at F. Keep going, just kind of pick the other one, x equals +1. Same argument either way. We're just trying to describe what happens to the second derivative, sign changes, and then justifying, well, if the second derivative has sign changes, there's concavity change, therefore we have an inflection point. So same idea. F double prime, we go from what, negative to positive. So that tells us that F goes from concave down to concave up. So we know we have an inflection point, change in concavity. And then similarly, x equals 3, just kind of pay attention to the signs. Your second derivative goes from positive to negative. So that justifies why the function goes from concave up to concave down. Therefore, justifying why you have an inflection point there. So if I had to kind of look at these three graphs and kind of decide what's a little more difficult for me to determine just by looking at the graph, I feel like part B might be the roughest because you're speaking about the derivative to address the second derivative. So practice that. It's pretty much the same thing we were doing in 2.2. It's just that sometimes with that extra derivative and thinking of it as another derivative could get a little confusing. But maybe you kind of have to rewind these so often to kind of get the analytical take. But really, it's the same thing we were doing with these computations, except that we had a formula to justify for us. Let's just do one last example to tie it up. Sometimes this depends on where your brain thinks, but sometimes the analytical geometry part is a struggle and sometimes you like it. So it's half and half usually. So just one more, just to kind of give you a look at a graph, and they want to ask us about the local extrema. But this time it's asking for the local extrema of the original function given the first derivative. So you got to be really careful when you're interpreting these. This is the first derivative. So a lot of things you can do for yourself. If you know you're given the first derivative, you can go back and say, well, what do I know? What does the first derivative tell me in the first place? It's supposed to tell me about increasing and decreasing, and it's supposed to tell me about local mins and local maxes. So that's good because at least they're asking about the coordinates of the local extrema. So what I like to do, if I'm talking about the first derivative, I might look at, well, let's just kind of name where it's positive and negative to start off with. And so if we're only viewing the first derivative and we want to speak about where it's positive or negative, well, look at where is the graph above the x-axis. Looks like from here to here and from here to here. So you could separate. Also, the graph is below the x-axis with the teal parts. So what I'm talking about above and below axis, I'm talking about, do we have positive y values or negative y values? So pretty much, you could kind of see that the x-intercepts or the roots of the first derivative are separating the x-axis up into 4 different regions. Oh, that was exciting. Hold on. We're actually in 3.3. There we go. So if you're looking at what's happening to the y values in the yellow region, your first derivative is greater than 0, i.e. positive. You have positive y values. So in both cases. Now in the teal region, your first derivative should have negative values. All those y values are below the x-axis. So that's where we're seeing the negatives. So now that actually tells us more information now. First derivative tells us information about the function, whether or not the function is increasing or decreasing. And when the first derivative is positive, the function is increasing in that region. When the first derivative is negative, it's decreasing in that region. So now all you have to do is see if there's any change of increase to decrease. And we see it actually. So at x equals, was it -1? Maybe I'll even kind of color code this as I have. So that's x equals -1. It goes from increasing to decreasing. So what does that look like to you? We go f prime goes from positive to negative, or increasing to decreasing. F goes from increasing to decreasing. So we have ourselves a local max at f of -1. Now, don't we have another place where it's increasing and decreasing as well? Yeah, over here. What's that x value? X equals 3. So same story. If you want to justify this for us, your first derivative goes from positive to negative. So that gives us information about the function going from increasing to decreasing. So then that finally tells you you have a local max at the function evaluated at 3. And then you just gotta see, am I missing anything? Yeah, I'm missing, where am I going from decreasing to increasing? I have a point right here. And if you're going from decreasing to increasing, it looks like at x equals +1, your first derivative goes from negative to positive. Sorry, I got a little excited on the signs there. I'm gonna make that a little bit nicer. Negative to positive. So that gives you information about the original function going from decreasing to increasing. So that tells you that you have a local, if you kind of look at your picture, yeah, local min at your function, original function evaluated at 1. So it gives you information. Notice, though, at your points, I've already colored this a lot, but when you saw x equals -1, x equals +1, x equals 3, that was where your first derivative was 0. So that's indicating that these points, these x values, are critical numbers, but we're not sure if they are giving us local mins or local maxes until we see the sign change of the first derivative. So that's why we had to further investigate. Now, just a little note at this point. At this point, because we don't have any information about the original function, we would not be able to find the y values. So we don't have enough information. To find the y values that we have just listed, what, f of -1, f of 3, and f of 1. So if you can do things with algebra and calculus, that's great. But a lot of times when you analyze the graph, that's also going to make this concept a little more clearer if we can kind of think about it in two different ways. So this one's a lot of good practice. I think you probably want to go start on the homework to further solidify these concepts. And I will see you next section.